Evaluating the fate of stream loss in the Snake Creek drainage basin using dual bromide and dye tracer injections in Great Basin National Park. Great Basin National Park is located in the southern Snake Range in eastern Nevada, a few miles from the Utah border. Water resources in the southern Snake Range are important for use inside and outside of Great Basin National Park. High altitude areas within the park are the headwaters for perennial streams on the flanks of the southern Snake Range and serve as the primary recharge areas for alluvial aquifers in adjoining basins. Ranchers in the towns of Baker and Garrison use surface water that originates within the park boundary for irrigation. Streams in the northern half of the park are typically perennial, whereas streams in the southern half of the park are intermittent or ephemeral, indicated by the dashed and dotted lines. The nature of the streams in the southern Snake Range is primarily a function of geology. A detachment fault, shown here as a thick black line, is a large-scale, low-angle normal fault that in this case runs approximately east-west through the middle of the southern Snake Range and Great Basin National Park. This detachment fault essentially divides the range into two geologically distinct areas, where the northern half of the park is primarily composed of low permeability metamorphic and intrusive rocks such as quartzite and granite, and the southern half of the range consists of more permeable carbonate units. It is for this reason that streams in the north flow to the valley floor, while streams in the south are of an intermittent or ephemeral nature. We are currently working on a project funded by the National Park Service in the Snake Creek drainage. Snake Creek is the most geologically complex drainage in the park. It flows from its headwaters in a granite cirque and across an intensely faulted area around the detachment fault and into carbonate. Snake Creek is perennial in its upper reach where it is underlain by granite. As soon as Snake Creek crosses the contact into the Pole Canyon limestone, it becomes a losing stream. In the 1960s, prior to the establishment of Great Basin National Park, ranchers who used Snake Creek surface water for irrigation in Garrison built a diversion pipeline adjacent to the stream to transfer water around the losing reach and return it to the stream channel 3 miles below. The pipeline is now in disrepair and is located within the boundary of what later became Great Basin National Park. Previous conceptual models of groundwater flow hypothesized that the detachment fault formed a barrier to subsurface flow and that Snake Creek stream loss likely flowed either south into neighboring Big Wash drainage or entered the regional flow system at depth. So what is the natural fate of Snake Creek stream loss? This is a photo of the diversion structure directing water to your right into the pipeline. Pipeline capacity is approximately 9 to 10 CFS. During high flows, when pipeline capacity is exceeded, Snake Creek overtops the diversion into the natural stream channel, as seen here during 2019 spring runoff. A reconnaissance dye tracer study was conducted in spring 2019 to investigate the natural fate of Snake Creek stream loss. The question was, does Snake Creek stream loss reemerge down gradient, and if so, where? Spring 2019 was a big runoff year which presented the opportunity to conduct a dye tracer experiment because stream water was overtopping the diversion structure and entering the losing reach. This slide shows an oblique view looking west up into Snake Creek and Big Wash drainages. The injection site is indicated with an arrow at the top of the Snake Creek drainage. We monitored springs, wells, and gaining reaches of streams with charcoal packets known as bugs. Fluorescein dye absorbs to the charcoal in the bugs, which were swapped every 2 to 4 weeks throughout the test. During the 2019 tracer study, no dye was detected in the Big Wash drainage, but we did detect dye at 2 sites in the Snake Creek drainage, both below the detachment fault. Squirrel Springs and Spring Creek Spring are located 1.5 and 6 miles below the point of injection, and dye was detected at each of these locations within 2 weeks of the injection. The results of the reconnaissance study are qualitative, only indicating the presence of dye and not what fraction of dye is recovered. In October 2020, we conducted a second quantitative tracer study this time using both bromide and fluorescein dye. The objective of the quantitative tracer test was to determine the fraction of stream loss that reemerges downstream. ISCO autosamplers were instrumented at Squirrel Springs and Spring Creek Spring, where dye was detected the previous year, and spring discharge was monitored with a flume. Based on the previous year's tracer study, dye was not expected to reemerge in any other sites, but charcoal bugs were placed in the other sample sites within the Snake Creek drainage to confirm that dye did not reemerge at any other locations. Dual tracers were used because each has advantages and disadvantages. Bromide typically has low natural or background concentrations compared, for example, to chloride. It is detectable in parts per million, and it is a conservative tracer, meaning that it does not react or degrade. Fluorescein dye is a powerful tracer because it has a very low detection limit, on the order of parts per billion. However, it can be problematic because of absorption and degradation. Although the dye results are not yet in, it will be interesting to compare the two tracers in the near future. The first tracer study in 2019 was conducted during high flows of spring runoff, in contrast to the more recent study in 2020, which was conducted during base flow. Prior to the test, there was no flow in the losing reach of Snake Creek because all of the base flow was being diverted into the pipeline. We obtained permission to turn the diversion headgate on October 2nd, 3 weeks before the tracer injection, releasing all of Snake Creek base flow into the losing reach, approximately 0.8 CFS. We did this in order to prime the system and get as close to steady-state conditions as possible prior to the tracer injection. Looking at the hydrographs for wells 5 and 8, we see the rising water levels in response to Snake Creek stream water released into the natural channel. Additionally, Snake Creek goes dry again in 2 locations below the pipeline, indicated by red X's. The dark blue dots show the advancement of stream wetting up gradient between October 2nd and November 24th. Squirrel Springs was one of the 2 locations where dye was recovered during the 2019 reconnaissance dye tracer study. The 2019 study was conducted in the spring during high-flow snowmelt runoff. During June 2019, Squirrel Springs discharge reached up to 18 CFS. During the 2020 tracer study, which was conducted during baseflow conditions, Squirrel Springs never flowed. One of our colleagues, an avid caver, army crawled 40 feet to the back of the cavern to confirm. But let's look at the results for Spring Creek Spring. This slide shows the breakthrough curve for bromide at Spring Creek Spring. Bromide concentrations are on the y-axis in milligrams per liter. Tracer was injected on October 21st. First detection occurred on October 31st, 10 days after the injection. The maximum bromide concentration reached 0.9 milligrams per liter, and this occurred on November 2nd, 12 days after the injection. Using an exponential decay function, concentrations are expected to fall below the detection limit on January 20th, signaling the end of the test. Total mass recovery is calculated by integrating the concentration times the flow. The total mass of bromide recovered as of November 25th was 25 kilograms. With an initial mass of 194 kilograms of bromide, this accounts for 13% recover according to the data so far. If measured bromide concentrations stay above the detection limit until approximately January 20th, as shown on the previous slide, we expect to see a total recovery of approximately 18%. The top hydrograph shows discharge at Spring Creek Spring in CFS. Spring Creek Spring, which was on a declining trend, began to rise around October 12th, 10 days after the Snake Creek stream loss was introduced to the losing reach. Note that this is the same period of time it took for bromide to reach the spring after the tracer injection. The estimated increase in Spring Creek Spring discharge is between 0.25 and 0.38 CFS. The bottom hydrograph shows Snake Creek stream discharge measured at a weir maintained by the Nevada Department of Wildlife Fish Rearing Station. During base flow conditions, flow in this part of the channel is supplied entirely by spring discharge from Gruden Spring above. The decrease in flow in the main channel, measured at the Endow weir, is equal to about 0.32 CFS, which corresponds to an increase in flow at Spring Creek Spring. This suggests that although not all tracer was recovered from the tracer injection, there was in fact no net loss in the system. This is further confirmed by preliminary data that indicates that Snake Creek flow measured downstream near the Utah border did not change after redirecting flow from the pipeline to the natural stream channel. In conclusion, contrary to previous conceptual models, Snake Creek stream loss crosses the detachment fault and reemerges at Spring Creek Spring and Squirrel Springs. During base flow conditions, we expect about 18% of stream loss is recovered at Spring Creek Spring. Increase in discharge at Spring Creek Spring corresponds with a decrease in discharge at Gruden Spring, indicating no net loss from the system. Our future work includes completing the rest of the bromide breakthrough curve once we receive the rest of the data, and comparing the bromide results to fluorescein dye tracer results to see if the fraction of recovery is the same for both tracers. Thank you for your attention, and I hope to see you at the Q&A.